Okay, well, we're going to deal with excavations and trenching today. So, during an excavation involving the removal of earth, that means 19 inches deep or more, this creates a depression in the ground or a hole, and you also create a pile of soil, which is known as a spoil pile or spoils. A trench is a special type of excavation that is deeper than it is wide, but no wider than 15 feet. So making this hole in the ground can create extreme pressures that are generated on the excavated walls of this trench or this excavation. If the walls are not properly secured by either shoring or shielding, which is like a trench box, or sloping, those walls will collapse. The collapse of the unsupported excavation walls can instantly crush and or bury workers alive. 1 cubic yard of earth weighs about 3,000 pounds, depending whether it's made of rock or clay and such. Depends on the materials. There are 3 different types of soil besides solid rock: type A, B, and C. Type A soil is more stable than type B soil, and type B soil is more stable than type C soil. So over here on the left, we see 3 trench profiles. The top one is type A soil, type B is the next one down, and type C at the bottom. These are slices through a trench, kind of a section slice. So we're looking down the end of the trench. Now in this case, they've got a trench box in there, and then near the top of the trench box, they've sloped the ground away. They have combined sloping and shielding. You can combine different systems together, but if there's sloping involved, you can go no deeper than 20 feet. That's an important factor. So you see that over here on the left side, 20 feet max in each one of these 3 cases. Now the other thing is that in each one of these cases, we've got this little unit triangle that is telling you something about the slope. So for every foot down, in every case is a foot down. For in the type A soil, for every foot down, you need to go over 3/4 of a foot at least to give you that slope, that 1 to 3/4 slope, which is about 53 degrees. In type B soil, it's not as structurally sound, so that you need to go over more. So for every foot down, you need to go over not 3/4 of a foot, but over 1 foot. So that's a 1-to-1 relationship. That's a 45-degree angle. And then for type C, for the worst case scenario, for the least structurally sound soil, for every foot you go down, you need to go over 1.5 feet. So that's a gentler slope again. So that's actually about a 33.5-degree angle or so. So those are the 3 types of soil and the 3 types of slopes that go with them. So that's an important little thing to think about. So let's kind of look at this thing about the soil. Soil hazards, cave-ins due to trench failure. There's falls from workers too close to the trench edge. You can fall over the edge. There can be flooding from a broken water or sewer main. There can be other reasons why you have sudden water in there. I remember when in my youth, being on a job site where we dug in at the far end from where we were working. The track hoe had dug into a underground stream, and suddenly this thing filled up with water within a minute or 2. It was amazing. So that can be you got to be able to get out of that trench quickly when you got a situation like that. You can have electrical shock from maybe striking an electrical cable in the ground, in the trench, or maybe striking one overhead by heavy equipment above you or something. You can have confined space hazards and confined space and atmospheric hazards in a trench, depending on the size and the characteristics and the air quality of the trench or the excavation. Toxic gas or liquid leaks from nearby facilities or underground pipes could cause a hazard. You could have auto traffic if you're near a roadway where maybe they end up in the trench with you, you know. And you can have falling dirt or rocks from an excavation wall or from an excavator bucket that could come down on the people that are working in the trench. Now, looking over here, you see type of soil and the number of failures, and to see how clay and mud, wet clay, creates the worst number of failures, 32 failures, compared to sand and gravel that only gets about 2 failures on average in the same numbers, in the same scenarios. Well, sand and gravel isn't particularly stable, but it sloughs right away, so it doesn't fool you. Whereas clay, when it's dry, can be as hard as a rock. If it's bone dry, the electrostatic forces hold the clay particles together, and it can be right like rock. But if you get water in the bottom of that trench, it can wick up and change the nature of that trench. And that happens a lot. You dig a hole, and next thing you know, you've got water in it, and then the water can wick up the sides, plus it can migrate through, and the trench walls can change from a type A soil to a type C soil if you're not watching and inspecting regularly. So that can be a hazard. So first of all, a little bit about soil mechanics here. You know, gravel is about, on average, 10 times bigger than sand. But you see, sand is not a homogeneous thing. You're looking at a zoomed up version of a coarse grain of sand, and then here's a fine grain of sand. So you can see there's a lot of difference between different sand particles, depending on what kind of sand you're dealing with and such. And then silt is 10 times smaller on average than sand particles, so they're much smaller. You see how small that grain is of silt. But these are all generally round particles. Now, they're nuggets. They're not necessarily perfectly round, but they can be. And the same thing is true with silt. But when you get to clay, it's 10 times smaller than silt, and you can hardly see. That's a coarse clay particle. Here's a fine clay particle that you can't even see. I don't see anything. Well, the thing about clay is it's not even round. It's leafy. They call them flat plate-shaped particles, but they're not like chevrons or plates. In that sense, they're more like cabbage leaves or something. You know, so if you go back to the larger particles beyond gravel, we've got boulders. They're too big to lift with one hand. They're two-handers. They could be like a watermelon or something. A cobble, the next one down, can be maybe some of these smaller ones you might be able to pick up with one hand, might be kind of like a cantaloupe or something. So a cobble is a one-hander. Gravel, nuggets like this, they're individual pieces or particles, you could call them. They're nuggets that you can pick up in between your thumb and your forefinger or other fingers or whatever, but they're small enough to differentiate with fingers and pick them up. So that's gravel particles. Now, when you go to, you know, there's the back here I had fairly round and fairly sorted size, or close to the same size, these nuggets here. When you get crushed gravel, we often have a much wider range of sizes. So these are, and then when they're crushed, they're angular. And angular gravel makes for much stronger, structurally sound roadbed or foundation to build on, because the angular pieces interlock, and that makes them more stable even on a bank. But and then when you go to sand particles, those are 10 times smaller than gravel particles, and that would be, well, we talk about gravel and as being coarse aggregates and sand being fine aggregates, but aggregates are what we normally build with, and we don't do a lot with silt and clay other than maybe try to prepare a foundation for the foundation. This picture right here, we're looking at, you know, by the naked eye. If we zoom in on sand particles, they look a lot like gravel particles. They're still nugget shaped, not chicken nugget shaped, but nugget shaped alone. And now if we zoom in closer to particles in silt, they can look a lot like sand particles, although they're not very colorful here, maybe with the microscope we're using, or I'm not sure. But silt particles are just much, much smaller. They're 10 times smaller than sand particles on average. And so so far, everything is about size of the boulder compared to a cobble, compared to the nugget for a gravel particle, compared to sand particles, which you can't really pick up an individual particle of. And then silt, you can't even really see the particles hardly. And by the time you get to the clay particles, you can't see anything. It's just dust. When you start looking at clay, this is clay. This is what clay looks like when you zoom in on the microscope. It looks like a bunch of cabbage or lettuce leaves all piled up. That's some kind of a dish. That's weird, eh? So clay is not only smaller particles than silt, their shape is very flat. It's like when you roll out a pie crust, you can have a ball that has a certain surface area. When you roll that pie crust out of dough into a flat pizza or whatever, you're gonna have a much more surface area. And that's what happens with clay. It has so much surface area that water, when clay is wet, has the ability to affect the size of clay. It actually tends to increase in size. Its volume increases when it's wet and it shrinks when it's dry. So that's a problem too if I get into the structure side of these things. Now, while I'm talking about this, I want to mention a couple other categories that are not looking at specific types of size so much as it's talking about mixtures of soils. Down here at the bottom, loam. Loam is really a term for talking about a mixture of sand, silt, and clay in various combinations. If it's really a perfect balance, it's just loam. If it's more clay than anything else, then it might be called a clay loam. If it's more sand than silt and clay, then it'll be called a sand loam. If it's a silt loam, well, it's got more silt. So nothing fancy about that. It's just what's the predominant material. But if it's a perfect mixture, it's just called loam. Or if you don't differentiate, it could be called a loam. And then submerged soil, that means it's wet. Submerged soil, when you're talking about particularly clay and silt, it behaves very differently than when it's dry. So when you're looking at the gravel particles here, they're about 10 times smaller than the boulders and cobbles on average. It's really focusing on the cobbles, I guess. Sand, about 10 times smaller than the gravel. Silt, roughly 10 times smaller than the sand particles. Here's some silt, and here's some more silt in the hand. When it gets wetter, it gets a little muckier. When it gets a lot wetter, it can hold a lot of water in it because the smaller the particle, the more surface area there's involved, and they have more area to cling to water, and that affects the behavior of the material. And here's some silt if it's dried up. It's not as hard as clay, but it can still be something that you wouldn't want somebody to take a piece of this and chuck it at you. It could still hurt like a rock to a degree. But when you get to clay particles in the wild, in mountainous areas, you can have faces that look like rock faces. When you get up to them, you realize it's just clay, but it can be as hard as rock when it's dry. There's electrostatic forces that can hold it together. And so if you have a clump of clay roll down on you in an excavation, it can be like having a boulder strike you. It can hurt. And when you look at clay, in Louisiana, we can carve clay. It's really usually a combination of clay and silt. And you can literally carve it if the ground is dry enough. You can carve and shape it to the point where you don't have to form with concrete forms. You can use the dirt. It's usually a matter of timing and watching the weather to do this. But it is a magical thing that you just can't do in other parts of the country. You just can't do that. This is, a huge advantage we have here in construction, in foundations. When you get clay wet, though, it's got to be the worst material to deal with. Oh my goodness, it's like goose poop. It's a mess. So wet, it's disaster. And it expands. So underneath concrete slabs, for instance, when the clay gets wet, it actually uplifts. It can lift up the slab, and when it shrinks down, it can leave cavities in behind. So if you've got a concrete slab that's 10 years old, you can take a 2x4 vertically and bounce it around. You can hear places where it's hollow underneath your concrete driveway. So the types of soil here, well, I've got a picture on the left here of these 4 different categories, but over on the right, I've got kind of a loam triangle, basically. And it's showing the clay at the top, the silt on the right, and the sand on the left, and then mixtures in between. And so that is another way that we look at it by the percentages to understand your soil, because in Louisiana, we have whatever the river deposited sediment, and mostly it's clay and silt and clay and silt and more silt and clay everywhere. But there are pockets of gravel and sand in the river, or where the river used to be, that collect in the elbows of the river. Sand and gravel collect. And so we get, some random amounts of sand and gravel, but a lot more clay and silt. Because that's what the river can transport the easiest down the river and deposit over the eons to create Louisiana and much of the central part of the United States. Anyways, when you're on a job site, you can't really tell what you got. You can test this simple ribbon test. Now, my dad used to put soil in his mouth. He was a structural engineer, and he would go on a job site and put a little of this in there, and he wasn't trying to taste it per se. He was trying to feel it. In your mouth, you can feel texture more than you can, on your fingers and your hands and stuff on your outside of your body. You know that when you get a single grain of sand in your mouth, you can feel that like a marble in between your teeth, So anyways, he was trying to test the texture to figure out if there's a lot of silt or clay, and you had to get a bit of experience to do that. I don't recommend putting any of that in your mouth. There are some weird diseases you can get from the soil, like staph infections and everything else. So no, don't do that. But there is the ribbon test. In the ribbon test, you make a ball of the soil. You need to have enough moisture in the soil for it to be like Play-Doh, so you can knead it around. You might have to add a little bit of water to get it, so you can kind of roll it into a cigar kind of shape. And then you start squishing it like you see in these pictures. Just squish it out past your thumb over top of your side of your index finger, trying to make a long little turd. Well, no, they don't call it that. They call it a ribbon. It sounds better. But they're trying to see how long you can make it. And the longer you can make it, the more clay that there is in that sample. If there's a lot of sand in it, you're not going to make anything. So down here at the bottom, they're trying to make a ribbon with sand and a little bit of clay and a little bit of silt, and you're not going to get very far. So, and if you've got a lot of silt, you might get little pieces that you can form, but not long like you can when you've got clay. So there are actually charts you can have on the job site to compare your sample to get an idea, measure it even, whether you got clay loam, sandy loam, loamy sand. There are real categories, and these names actually have real meanings in the soils analysis industry. Not that you have to be an expert on this, but for the safety and understanding your excavation, I recommend taking, I don't remember the course number, but there is advanced OSHA courses in excavations and trenching, which can really help you. It's a real eye-opener, and it can really help you out. But what I've got in that side of this presentation gives you an awful lot too if you spend the time to study it. Yeah, okay, so soil with a high sand content won't form any sort of ribbon at all. Soil with a high silt content will form flakes or peel instead of forming a ribbon. And of course, soil with a high clay content makes a long ribbon. So you get the idea. And then there are categories of, when you talk about sand, there's a real meaning from what that is. You can't get a ribbon at all over on the left, and sandy loam all the way down this page. And then down, there's a page 2 over here where you're looking at silt and clay loam, clay, organic soils even. So organic soils can also give you some amount of a ribbon, because of course you get all this organic biological material in there, but we never build on organic material. We always strip off the topsoil first. You might save it so you can do some gardening and a little landscaping afterwards, but we don't build on biomaterial, on organic material. It deteriorates over time and the building sinks pretty quickly. Within a year or so, you can have this kind of an action. So it's, we got to get rid of that and get down to solid material at the very least, even if it is clay. The behavior of the sandy soil and the wet loam, the sandy soil tends to collapse straight down. So like the diagram you see up top. The second one down, wet clay and loams tend to slab off the side, and so you can end up a piece that's not visible from the top that can come off and get you. Looking at dry, firm clays and loams, they tend to crack back further, and you get these stress cracks further back. And then the wet sand and gravel tends to slide off as a big slump. Now, to back up to this picture, this guy in this photograph here, he's looking up. It's all kind of a fun little picture. This is the last picture of this guy alive before his trench collapsed on him. There's no shoring, there's no sloping, there's no trench box. And yeah, you think you can trust it because it all seems very permanent. But clay in particular can trick you. It's kind of the schizo material. It can change from one to another without you even realizing it. And so you've really got to watch your trenches throughout the work that's going on in the trenches on an ongoing basis, not just at the beginning. And here's another guy who's actually digging out somebody else in here and himself. And everybody's standing around watching because, when there's a rescue, they often take 8 hours to do a body recovery or a rescue if this person is buried up to their chest, because when the rescue people arrive, they're not going to even go in there until they've built a temporary shoring system to get in there. Okay, here's another crazy couple of cases. There's actually two pictures here. It almost looks like one. It's not the same bad job site, there's two. But there's no egress. There's no shoring. If you've got a trench or an excavation anything deeper than 4 feet, you've got to have egress. That means ladders or stairways or ramps dug into the ground. Most of the time it's going to be ladders. And then if it's more than 5 feet deep, you've got to have shoring or sloping or a trench box. And these pictures, neither one of them have any of this. So yeah, okay. So, conditions that can lead to a trench failure: disturbed soil from previously excavated ground, trench intersections where large corners of the earth can break away on you, a narrow right-of-way causing heavy equipment to be too close to the edge of the trench for a particular period of time, vibrations from construction equipment or nearby traffic or trains, pile drivers, compaction equipment. That would be the examples of construction equipment. The next one down, increased subsurface water can cause soil to become saturated and therefore unstable. Drying of exposed trench walls can cause the natural moisture that binds the soil together to be lost, and you can get peeling away of dry material that was just only being held together by the goo. So that's kind of the opposite of the problem of wet, which is mostly the problem usually with trenches where they get wetter and wetter. Inclined layers of soil that are dipping into the trench can cause layers of the different types of soil to slide in one upon another, causing the trench walls to collapse. These are all different scenarios. So these are some of the pictures maybe showing some of that. Tension cracks, toppling, subsidence and bulging, sliding, heaving, or squeezing. And then there's kind of the boiling. There's not really boiling water or anything going on there, but it can look like boiling almost as the soil is, water pressure is pushing the bottom of your trench upward. Now here on the left, I've got a picture of an excavation. An excavation is the general term for any depression in the earth that we make, but with trenches, they are deeper than they are wide and no wider than 15 feet. Well, this picture on the left is way wider than 15 feet, but it has all the hazards of a trench because it is so deep. We're allowed to have benches like you see here on the side, but not like this. They can only be 4 feet high. So this is maybe 14 feet high. And do you see any kind of ladders or egress? There's no place to go except to run up past the excavator and past that dump truck up that driveway. So you got to have ladders if this thing is more than 4 feet deep. There's no shoring or sloping, really, not enough sloping anyways, and a benching is out of this world. It's way, OSHA would shut that down for sure. And then over here on the right-hand side, we've got a trench. You can understand why they might dig a narrow trench to not have to dig up too much roadway. But they can't just live with that. This thing is definitely more than 4 feet. They need ladders. It's more than 5 feet too. It's also more than 5 feet. So they need either shoring or a trench box. Now they might have a hard time putting trench boxes in with all that pipe in there, but they needed to build shoring and they didn't do that. And so OSHA would shut this job down. Even if it's a government job, OSHA still can issue citations. Where's the egress? Where's the shoring? Where's the shields or the sloping? You got to have something. And if this thing was deeper than 20 feet, I don't know, maybe it is. This thing could be more than 20 feet, actually. Probably is more than 20 feet now that I look at it, trying to judge it all. Then you can't do any sloping. You can only do shoring or trench boxes if you're more than 20 feet deep. Okay, so you never enter an excavation without the approval of the competent person on site, the competent person for excavations and trenching. Someone must inspect the excavation daily and throughout the day for changes in the excavation environment, such as rain and frost or severe vibration from nearby heavy equipment. Never enter an excavation until it has been inspected and all required permits have been obtained. That means the next day when you go into an excavation after working in it the day before, you need a new permit. You got to wait for that. If you try to go in there before somebody's tested for air quality, you could have gases that are heavier than air that subside and collect in the bottom of that trench. And you walk in there and pass out and nobody notices for a while, it could be all over. Wear protective clothing and equipment such as hard hats, safety glasses, work boots, and gloves. Use respirator equipment if necessary. Wear traffic warning vests that are marked with or made of reflective or highly visible material if you are exposed to vehicle traffic. Get out of the trench immediately if water starts accumulating in the trench or if any other hazard develops. You do not walk under loads being handled by power shovels or derricks or hoists. You got to watch for that. Stay clear of any vehicle that is being loaded nearby. Be alert and watch and listen for possible dangers. Do not work above or below a coworker on a sloped or benched excavated wall. Barricade the access to the excavation to protect pedestrians and vehicles. And check with your supervisor to see if workers entering the excavation need excavation entry permits. On some jobs, you may not. In the plants, you almost always do. However, I've got this other thing. It's something that NCCR likes to say. They say ladders and ramps used as exits must be located every 25 feet in a trench that is over 4 feet deep. The numbers are correct. The wording's not quite right. So I put an X in there. No, that's not the way it's wording. But NCCR could ask the test question this way, so you still need to be familiar with it enough to understand what they're saying. The true standard, what OSHA says, is that ladders and ramps used at exits must be located within 25 feet of each person. So not located every 25 feet. It means in a trench, you could have a ladder every 50 feet and you would always be within 25 feet of a ladder. So within 25 feet of each person. That's what it actually says in the standard. If it's over 4 feet. So once you're even a smidgen over 4 feet, and in a trench they can find a place where it's going to be over 4 feet if you're trying to go for a 4-foot trench. So that means when you get to 4 feet, you should be already providing ladders long before that as a best practice. But NCCR might not just make that distinguishment, and so don't fret about it. If they've got 25 feet and 4 feet in the question, then that's right, as far as they're concerned, for that day anyways. Now, there's nothing wrong with, what they're saying is really stricter, and there's nothing wrong with doing that. Nothing wrong with having twice as many ladders in there as what's required. But I just want you to know what the standard truly is. Okay, so this picture on the bottom right corner kind of shows that. If you've got a ladder every 50 feet in a narrow trench, yeah, you're always going to be within 25 feet of a ladder. Other ladder rules also apply here. That means you got to have at least 3 feet of ladder sticking up. So here, they're not complying with the 3-foot rule in this trench here. They haven't finished backfilling around it and stuff. Whatever's going on, I'm not quite sure in here. So they're not finished either. Here I've got better wording because really and truly, it's probably better for you to think about the 4-foot rule first. So, and I've basically taken the same thing that was on the previous page about in the white lettering here and reworded it better. In trenches or excavations deeper than 4 feet, ladders and ramps used as exits must be located within 25 feet of each person. That's a better way to remember that statement, I think. Okay. You make sure that someone is on top to watch the excavated walls when you enter a trench. Make sure you are never alone in a trench. 2 people can cover each other's blind spots and see stuff. You should keep the tools and equipment, even your lunchbox, and the excavated dirt too, the spoil pile. It should all be at least 2 feet from the edge of the excavation. Now that has nothing to do with the weight of the trench. Let's say the spoil pile could cause the trench to collapse. And the 2-foot rule has nothing to do with protecting it from that. It's just about not having something accidentally fall in the trench. You don't want anything, lumber, tools, anything to accidentally come rolling down into that trench and hit you on the head. Make sure that shoring or the trench boxes, the benching or the sloping are used for the excavations and trenches if you're over 5 feet. So we have a 4-foot rule for needing egress, ladders usually, for entering and exiting. And mostly we're focusing at the exiting in the emergency. And then that's the 4-foot rule. And for the 5-foot rule for excavations are that you have to have shoring or trench shields, trench boxes, or sloping or benching in some cases. So benching and sloping are kind of in the same category, except for type C soil, you are not allowed to do benching at all. So that's why sloping is kind of the thing we say. But benching is kind of a form of sloping that's only allowed in type A and type B soil. So that'll come up in a minute here. Stop work immediately if there is any potential for a cave-in. Ensure that any issues are resolved before resuming work. Okay, so ladder requirements in the trench is the same picture down below, and the other part is kind of showing you the 2-foot rule here. But it's just kind of reviewing some of these rules here. Ladder side rails must extend a minimum of 3 feet above the landing, which is the top of the trench, But if you're talking about benches, then you're going to have a ladder at each one of these benches. So then each top of a bench is another landing, Ladders must have a non-conductive side rail if work will be performed near the any kind of electrical equipment or systems using electricity. Ladders and ramps used as exits must be located within 25 feet of each person in a trench over 4 feet deep. Okay, well, I've said that about 3 times now at least. This is a new one that's related. Still 25 feet in the question or the answer. And that is that 2 or more ladders must be used where 25 or more workers are working in an excavation, which ladders serve as a primary means of entry and exit. So if you get 25 or more workers in a trench or an excavation, you got to double up your egress. This is also true when you got a bunch of people working on a roof. You got to think about that. You got to have ladders on your roof for egress to get off of that roof. The opposite of getting up out of a trench, but it's the same concept. And the same thing goes for 25 or more workers up on a roof or on an upper level. All ladders must be inspected before each use. So that usually means daily. Damaged ladders should be labeled "Do not use" and removed from service. Use ladders only on stable or level surfaces. This is all common sense about ladders that applies in all cases, including excavations. Secure ladders when they are used in any location where they can be displaced by excavation activities or traffic. So you've got to kind of make sure these ladders continue to be stable. While on a ladder, do not carry any object or load that could cause you to lose your balance. We're not really supposed to carry anything when we're climbing ladders. Exercise caution when using a trench ladder. So I've talked about the shoring and the sloping and the shielding, but let me formalize that here. Shoring, you're talking about a built-in place structure. And I could describe more, but that's enough here. Shielding, we're talking about a prefab structure. So the trench box is a prefab structure you pick up with a track hoe or a crane or something and you drop it in the hole. By the way, you've got to backfill around it before you can let anybody in there. You cannot just drop it in there and declare victory and let somebody get in that trench box. You've got to backfill around it. People have been known to lose their legs when the trench collapses and shoves the trench box sideways, and the whole trench box mows over your legs. And then down here at the bottom, sloping. It's a technique that employs a specific angle of incline or a specific angle of repose on the sides of the excavation. So that language may show up in other places here, so it's good for you to kind of be familiar with it. If the angle of incline or the angle of repose is the same angle. It's a matter of whether you're standing at the bottom of the trench looking up the slope, that's the angle of incline, or if you're at the top of the trench looking down, it's the same angle from the horizontal down as it is from the horizontal looking up, but we call it the angle of repose when you're looking down. Same angle, it's just, it could be described either way, depending on the situation. So this angle varies based on the assessment of the impacting site factors. Again, what type of soil you have. So type A, B, or C soil. If you don't know what kind of soil you have, if you don't have somebody who can determine whether you have type A, B, or C soil, or if you just want to be on the safe side, you should always assume that you have type C soil, worst case scenario, and that way you can be safest. So if you do that, then type C soil means you cannot do any benching. That's one problem. The other thing is that does mean a gentle slope. Now, if you're doing shoring, it doesn't really matter as long as your shoring is strong enough. Sloping, though, if you're doing any version of sloping, you cannot dig any deeper than 20 feet. Anything deeper than 20 feet, and you're screaming to the world and to the world and to OSHA that you've got a trench or an excavation that's no deeper than 20 feet if you're doing any kind of sloping. If you've got benches, you're screaming to the OSHA inspector as you're driving down the road that you declare that your soil is not type C soil, it's type A or B soil. So shoring systems, we can use metal or timber or concrete uprights. The uprights are generally the sheathing, the plywood, the sheet piling. It could be concrete piles that are driven into the ground. It could be heavy timber piles that are driven into the ground. It could be a slurry wall that's been poured into the ground. And then you can do bracing, either diagonal bracing, or you could have tiebacks going back into the earth, or you could have cross-lot bracing going across the trench or something, But yeah, so shoring systems are built in place using uprights, and then you have whalers that kind of strap along there like reinforcing webs, horizontal, whalers are horizontal, and then braces. You can have cross braces or tiebacks. Those are all components that could be components of a shoring system. All shoring must be installed from the top of the trench down. That means you cannot jump into a trench and build the shoring system. You have to work from a suspended position above. It's kind of the reverse of scaffolding. Scaffolding, you have to work from relative positions of safety from the ground up, very methodically. From the position of shoring, you got to work from relative positions of safety up top and install the bracing, tiebacks, and what have you as you go down. There's a lot to that shoring system science. Here's a shoring system right here. An old-fashioned picture here. There's actually some people in here, but they can't get into here. You couldn't build all that bracing from down in here. You have to build it from up top, and that's complicated. Modern times we'll use hydraulic shoring systems so that we can dangle it with heavy equipment and get that shored up. And then as you go down in, you're putting pins in place for safety because you should never trust your life to hydraulics, just like you don't want to get up underneath a hydraulic piece of equipment that's lifted up, that if the hydraulics fail, it drops and gets you. So that's a shoring system. Here's a sheet piling system where over here on the right-hand side, I've got a pile driver that's driving piles of corrugated shaped steel piles into the ground close together. And a lot of times they'll space them out and go and then come back and fill in between and drive the piles to fill in the in-between part in a second pass. That just depends. And then they've braced it with some big diagonal braces going into the ground. That's done sometimes, but that stuff sometimes is in your way. And so tiebacks going back into the earth are another way. So there are basically three basic ways that you can make shoring strong so that it doesn't just collapse on you. You know, you can't, even a concrete wall is going to fall over unless it's tied or braced in some way. And so you can have cross-slot bracing like you see at the top, where it's an external brace, but that could be in your way of your trench or whatever, if depending what you're laying into the hole or what we're doing in there. Sometimes the rakers, diagonal braces, rakers is another name for that. Or you can have tiebacks that are going back at an angle into the earth, usually about a 30-degree dip going back into the earth to connect the earth to that connection to help hold it from collapsing. Those are tiebacks that are kind of put into the earth. A lot of times they'll drill right through the sheathing, whether it's piles that have been driven down or could even be a 3-foot thick concrete wall. And then they drill into the earth, and then they'll put a pipe sleeve in part way, and they put the same kind of cable that we use for post-tensioning, pre-stressing strand in there, and we pump in a grout and let it bulge to create a kind of an anchor like you see down the bottom here. And when that concrete is set up and bonded to the strands, then they can come out here and post-tension this to actively hold that tieback against the earth. That's how tiebacks work in the industry. I've got lots of pictures I could show you in here, but in the interest of time, I'm skipping past it. Here's a trench box, a shielding system. So when we talk about trench shields or a shielding system, more often in the industry, we nickname and shorten it to calling it a trench box. It's just much more common. But so you can have a single unit like this. If it's so, you'll have at the bottom, it'll have a fairly sharp edge on the bottom. Maybe not sharp to cut paper or cloth, but it's something you certainly don't want to get your foot underneath. They can kind of drop it in so it kind of lodges into the earth. And then they backfill before you can let somebody in here. Here's a different kind of a trench box. It's bigger and it's 2 levels. And so there are some trench boxes where you can have a second layer that's not pointy at the bottom that connects with the upper layer and to allow it to brace in place. Here's another system where they've actually got a guardrail that clamps to the top. That's kind of a nice idea. In this particular case, it's tight to the trench that they're cutting right up against, looks like concrete even, or maybe some concrete curbing, I don't know. But that's a trench box with a guardrail system. Here on the left, you got stackable trench boxes again. And on the center, you got kind of a hybrid system where you got some heavy sheets of some kind of steel, heavy steel plating that are dropped in with track hose or cranes and such. And then maybe with hydraulic shoring. I'm not quite certain if it's hydraulic or not. It looks like it could have been, but definitely the one on that was the one in the center. But over on the very right-hand side, that's definitely hydraulic shoring. And so they pump it up, but when they're going to climb in, they're going to stick pins in that would be safety pins, so that even if somebody accidentally cuts the hydraulics, this thing's not going to kill you. You know, you're safe because of the pins. So sloping system. Sloping is accomplished by inclining the sides of the excavation, or maybe a better language that NCCR more likely will use is cutting back the slope at an angle. They cut the slope with heavy equipment usually at a particular angle. The angle of incline varies according to those such factors as the soil type, the environmental conditions of exposure, and the nearby loads. So for instance, if it's the soil's getting wetter, if the soil type is changing, you've got to take that into account if that's going to be a problem. You may have to slope it that way to begin with if you're going to slope it at all. If you're not going to, so yeah, wet soil. And also though, if you had a foundation of a building that you're coming up close to, that's a supercharged load, a surcharge load. And so that requires maybe a steeper incline or maybe no incline. You might have to do shoring all the way up because of that. So there are 3 general classifications of soil types. I talked about them before. Here they are in the table up at the top. Stable rock. If it truly is stable rock, they can literally cut that rock at a 90-degree angle if it's stable. With type A soil, you can go steeper, 53 degrees up from the horizontal, so that's much steeper than type B soil, which is a 45-degree angle, and type C is a 34-degree angle. So in each one of those cases, the ratio is always in slopes. We mention rise first and run second. So for every foot down, that's the rise, or every foot up, if you're thinking about from the bottom. Either way, it's the vertical number first, and then the second number in the ratio is the horizontal number. So for every foot up, we go over 3/4 of a foot. With type B soil, for every foot up, we go over horizontally 1 foot. For type C soil, for every foot we go up, we go over 3/4 of a foot. They always usually focus on going down, but it's the same thing. That said, OSHA gets it exactly backwards. Nobody else does this. Carpenters always rise, run for stairs, for rafters, everything we do. Roof slopes. 5/12 slope on a roof is 5 inches up, 12 inches over. It's always rise, run in physics, in chemistry, in mathematics, except OSHA, the twerps. They get it backwards. They put the ratios opposite. So this table down here came right out of NCCR's book because they're just parroting back what OSHA says. It doesn't matter except that you need to be aware of the possible confusion that people could have over it. The only number that's changing is a horizontal number. As long as you remember that, you're never going to have any trouble with this. And when you know that type A soil is going to be the steeper number compared to type C soil, you won't get that confused either. But anyways, I just wanted to vent. Okay, so let's see. Looking back at this drawing that I have here again, I wanted to point out, notice something I didn't mention earlier, is that this trench box has to stick up 18 inches. It's a rule OSHA has. You've got to have your shoring or your trench box sticking up above the ground at least 18 inches, so that if anything does roll down this bank or fall in the hole, it's going to hit that top curb that's going to keep and protect people from stuff going into the trench and hitting them and striking them. So that's true. So if you cannot do any sloping, then you've got to go, the trench boxes have to go all the way up and 18 inches above the ground, because otherwise you're employing some kind of sloping. So always 18 inches up. And if you're talking about shoring that's going right to the ground level, no sloping involved, you still got to be up 18 inches above the ground. So that's another number. That's the thing about this particular topic, is there are so many numbers and classifications for you to know. And so within soil types, I've got them lined up in here again with these numbers. But there are some other things I want you to know. There's a couple other things about soil types I want you to know. So let's look at this. First of all, this is the slope of a type C trench, where for every foot we go down, we go over horizontally 1.5 feet. And so that's what kind of angle we get. The angle of repose is angle from the horizontal up top of the ground, dropping down. The angle of incline is where you're going up. And so from the horizontal on the ground, you're measuring this angle. Now, we don't find it most of the time easy to measure angles like this on a job site. You don't bring out surveying equipment for this kind of thing. It's more common to use the ratios. You pull the measuring tape out, you measure the vertical and the horizontal numbers in order to get that right. And I already mentioned, always assume worst case scenario unless you've got a qualified person who is your competent person to determine what soil type you have. And if you're deeper than 20 feet, you cannot do this. You've got to build a shoring system or install some trench boxes instead. If it's type A or B soil, you can do benching. And the way you do that is you zigzag all the way up like this. So you can only go 4 feet high. If it's type B soil, you go over 4 feet max. Then you go up 4 feet, and then you go over 4 feet at the most, and up. You can zigzag up. It's basically creating that same slope, but in a zigzaggy pattern. But yeah, 4 feet, 4 feet, 4 feet, 4 feet, all the way up. That's what you do for type B soil. For type A soil, you can still go up 4 feet, but now you can go over as little as 3 feet. So then it becomes 4 feet, 3 feet, 4 feet, 3 feet to keep that slope. You can go more. You can have a horizontal number more than 3 feet, but you can't be less. So that's what you do for benching. But you are telling the world when you start creating benches in your excavation that you've got type A or B soil, and it's going to stay that way. It's not going to be a problem. And that's often is a problem. In Louisiana, particularly in the plants right by the river, the water table, especially in the spring, is up high. The water just keeps migrating into it. So you got to keep the bottom of that trench dry. That means you find some place where that's lower than everywhere else that you can make the water go to so that you can keep pumping it dry as possible. So again, there's that 18-inch curve that you need to have in the trench. The 2 feet number here. So I've just got some of these things in review here. Stable rock, yeah, you can go 90 degrees many times. When the rock is structurally sound, you can cut it at a 90-degree angle. Clay, when it's bone dry, and there's been a few times over the many years I've been here in Louisiana where we've had a drought for months where the clay can get so hard that it's tough for the equipment to dig through it. That can be a type A soil. But if it's wet, it's not a type A soil. The clay and the silt become type C soils very quickly. There's exceptions in type A soil where you can even go steeper than temporarily for a single day, where you could go to a 63-degree angle. For every foot down, you can go over only a half a foot. That's a special case with extremely dry clay. Short-term excavation, you can have a much steeper, but you can only go 12 feet. So they have some special rules in there for it. So there are some exceptions. Those are not likely to apply in Louisiana because our type A soil can change to type C soil during the day. So it's just showing a lot of the stuff we've already looked at in here. One thing I wanted to point out, this in the language here that I've added in here on these pages here, the second time around here on the type A soil, is the load-bearing capacity of the soil. Type A soil, you can put per square foot, you can put 1.5 tons of load on it. That's what you prove. In fact, that's one of the ways we can measure the type of soil we have by taking a square foot concrete block that weighs, and oftentimes it means it's got other loads on it. They might even put some lead in there along with this block. But it's going to be a 12-inch by 12-inch square, or it could be bigger than that, but they're going to load it down with heavy concrete to get to the equivalent. But per square foot, every 12-inch by 12-inch space, you can put 1.5 tons, and it's not going to settle. That's 3,000 pounds that you're putting on 1 square foot of ground. That's pretty strong ground. So that's what it means to have type A soil, that it's got a load-bearing capacity of 1.5 tons per square foot. Now, when you go to type B soil, it's less than 1.5 tons, but more than 0.5 ton. So 0.5 ton is 1,000 pounds. So 1 square foot, you can put a whole 1,000 pounds on there and it's not going to sink. That's still pretty good ground. But that's what type B soil means, between 0.5 ton and 1.5 tons. And that's type B soil. Type A C soil means that it's less than 0.5 ton. Anything less, it could be 10 pounds it can take, and it's still type C soil. So it could be goose poop, gushy stuff that can barely support. You put your hammer on it and it sinks into the ground. It's like just horrible soil. So type C soil does not mean it's going to be that it can take 1,000 pounds. It could take up to equivalent of 1,000 pounds, a half a ton. But it could be 10 pounds is all it could take per square foot, and it still would be called type C soil. So all comers, all the worst stuff is type C soil up to 1,000 pounds. So type C soil includes things like gravel, loamy soil, sand, any submerged wet soil. So when you're looking on a test question with NCCR, if you see the word submerged or wet in the statement, that's a type C soil. So let me back up because some of those key words can be turned into test questions. You'll see them in my quiz questions. Type B soil includes angular crushed material, crushed gravel, crushed rock, unstable rock. So crushed or unstable rock. If you see the word crushed in the statement, that's a type B soil. There's multiple ways that they'll test you on this. So they look at the load-bearing capacity, the slope. That's why this section is one of the toughest sections, because there's just so many things they can ask you. So let me look back at the A soil. So here's the thing, is that I talk about how bad clay is, because when it gets wet, it's horrible stuff. It's dangerous. But dry clay is beautiful stuff. Wonderful stuff. The trouble is they won't mention that it's dry, but if they don't mention it's wet and they're talking about clay, then it's a type A soil. That's what you have to remember for a test question. But the reality is, what they should be saying is if it's dry clay, it's a type A soil. If it's wet clay, submerged clay, it's a type C soil. That's the nature of this stuff. Now, there is a thumb test. I don't think it's the best thing to use in the world, but it's good to know about it. That if you can press into the soil all the way to your knuckle, you've got type C soil. That's the bottom one. If all you can do is make a dent, it's a type A soil. And if you can get it kind of to your first knuckle or to the thumbnail, somewhere in that range, it's a type B soil. Now, some people have stronger thumbs, bigger thumbs, so all of this is kind of not the perfect test to use, but it's a system. I didn't say it's a good system, but it's a system. So it's good to know the thumb test. It's better than nothing. So, if all you can do is dent the soil, it's a type A soil. Now, there's something called the penetrometer, and the pocket penetrometer, the pocket soil penetrometer test, is almost like a screwdriver, cross between a screwdriver and a shiv. No, I don't know. The point is, it's a spring-loaded piston that when you push the soil, it'll measure how much pushback it got, and this little rubber thing will slide along to the mark on the scale to tell you. And it generally lists it in tons. The numbers are in tons per square foot. And if you're in type C soil, sometimes you have to use this foot in order to get any kind of a reading at all. To stick it on there and screw it on, to spread it out like a snowshoe. So that's a pocket penetrometer right there, and in these pictures right here. Now there is a plate load test. It's also for a type of a penetrometer where they usually stabilize it with a piece of heavy equipment. So they put a hydraulic jack down and stabilize it before they go and start pushing against the ground to measure their tests. So they can push down on the ground. This is often used at the beginnings of a job site when they're doing tests. And there's other tests, like I said, they can have a weight and they time it and put some heavy weight on a per square foot measurement to kind of measure. There's other kinds of soil tests, but they're all about load-bearing tests. So something as simple as a penetrometer is better than nothing, and that's way better than the thumb test. But I said there are some fancier tests that are done, and they can be called penetrometers also. The other thing we do on a job site when we've got to excavate is we can manage the water by pumping it out. I mentioned pumping it out of the trench, but another thing you can do is literally drive rods, pipe into the ground and suck the water out of the ground to artificially lower the water table. So that's what we call dewatering, when we dewater the soil by actually artificially lowering the water table. And so that's a process. You can use sump pump, well points, eductor, there's deep wells and stuff. They all do the same kind of idea. Here's an example of a bunch of well points into the ground, that I think they augered the ground and stuck those in there, and then they hooked them up to a manifold that goes through a bigger pump. So that's a little different system, but it's the same idea. But you know, in permanent high rises, many high rises are built on very soft ground, and they have to have deep foundations, and they have to keep those deep foundations dry. If you want to have a foundation, a basement in Louisiana, this is what you have to do, is dewater. Now, not so much like this. You're more likely to have a bunch of sump pumps in the building lower than the basement ground, so you can artificially lower the water table around your building. And so buildings that have that in Louisiana, and I know of a bunch of basements in Louisiana, they do exist. There's a bunch of them on LSU's campus, for instance, that I've been inside the basement and below the basement in the quadrangle and in the tunnels. They have a whole bunch of little bitty pumps all over the place, and so facility services has to go around and clean up and maintain those pumps because they get clogged after a while and stuff. Okay, I digress. So the rescues from trenches, just like with confined space rescues, excavation rescue teams must be specially trained and undergo regular practice. If your safety plan depends on an outside rescue team, don't assume your local fire department is ready. Some of them will be, some of them won't. And time means a lot. You've got to make sure that you're ready. So trenches collapse every day. On average, I said earlier, rescues take about 8 hours. And so here's a rescue going on. Here's a rescue. They rescued one guy who was buried up to his hips in about an hour and a half. And the other guy took 9 hours to recover his body. And he was laughing and joking about an hour after the trench collapse. But over time, he asphyxiated because it takes volume to breathe, and that's pushing on your chest and on your lungs, and you pass out eventually. And he lasted longer than some people may do. Here's another trench collapse. It was in Covington, Louisiana, back in 2015. This is the survivor here. The other guy died, and that often happens in trenches. One guy dies and the other guy survives. Not always, but it's like a mining accident almost when a collapse happens. And they typically happen because there was no shoring or sloping going on, or trench box, and that's why it takes 8 hours. Like I say, they go and build these rescues by building a shoring system. There's a bunch of trade terms in here. I think I need to set that aside. I've kind of defined some of these things along the way already in here. There's also 3 pages of summary, kind of in a summary here, that are really worth looking at. These all could turn into test questions, so it's really worth looking at these summary questions. But because I've gone so long, I need to kind of here's a really good thing on the 3rd page about the soil types, looking at where I underlined dry clay. Well, you might not see dry in the question, but clay as opposed to submerged clay, crushed rock, wet loamy soil, or submerged soil. These are keywords that'll help you. If you can memorize them, they'll help you with the test questions. So that's all you need to know about excavations and trenching.